Hi you guys, today we're talking about the distance formula, Unit 1, Day 5. Our objective today is that I can use the distance formula to determine the distance or length of line segments. Now we're getting close to the end of our unit now. We're talking distance today, equations of circles next unit, next class, and then we'll have our Unit 1 assessment. The statement of inquiry today has to do with the relationship between distance and time and how it develops the foundations for how we interact with the world. There are a lot of ways in which distance and time helps us with specific scientific concepts progress in our society. So for example, when you're driving, right, you know what speed you're driving at, you know the velocity, right? We all have that sense of what acceleration is. It's like as you're going faster and faster, it's that sense of being pulled back into your seat, right? Maybe when you're going on a roller coaster, you're going like through some sort of a free fall, you have a body intuition of what that acceleration feels like. And there are mathematical ways of describing that acceleration using numbers and specific variables. Similarly, force, work, and power are all physics concepts that you guys have an intuition about, right? If you push a wall versus if you pick up a chair or you carry your backpack, those all require force and work and power to interact. Another example is friction, right? If you are ice skating versus if you're using sandpaper to sand down a table or a chair, the concept of friction has to do with distance, right? And this coefficient of friction. Momentum is like the sense of wanting to keep going or making things harder and harder to stop. Kinetic and potential energy, magnetism, electricity, astronomy, art, and then the distance between atoms and molecules, so on a very, very minuscule level, have really big effects on chemical properties. So thinking about how thick of a coating to put on medication so that when you swallow it, immediately it doesn't taste really, really bad, but as soon as it starts, going into your body and you don't taste it anymore, it can start to dissolve so that all of the, whatever reasons you might be taking, ibuprofen or Tylenol or things like that can start working as a pain reliever. All right, so these are all examples and places in which this distance and time relationship builds a foundation for how we interact with our world. On a very just how we're thinking about things nowadays, public health experts are recommending 6 feet of distance between people to help contain the spread of COVID-19. But how do you know what exactly 6 feet is? Most people don't carry around rulers, tape measures, yardsticks. So what are the things that are kind of around us, or how can we use our bodies to figure out and estimate 6 feet, right? I think one of the ways that I think is I know how tall I am, right? So I know what my wingspan is, right? So I know it's going to be a little bit further away from what my wingspan is. Or I know that if you go grocery shopping, one of the common kind of mental tricks that they're recommending is to use 2 grocery shop carts, right? So if you're standing in line for for your groceries, you should be about 2 grocery carts away from each other, right? So there are ways to think about distance that's very intuitive. And what we're trying to do today is to tie that intuition with the mathematics so they help each other out and go hand in hand. Now, in order to do this, because the distance formula itself has a square root, we need to make sure we're comfortable with what that is first. Now, square root is the inverse operation of squaring. And when we talk about squaring, that is our little exponent 2. So if we saw, for example, 5 with that little exponent, we know that means multiply 5 by itself 2 times. 5 times 5. And we all know that's 25. Right? So the inverse of that would be, well, if we have 25, what number, when you multiply it by itself, would give us 25? And so we know, well, from 25, if you do 5 times 5, you get 25. So we get 5, which means the square root of 25 equals 5. So they're inverse relationships, the same way that adding and subtracting are inverse relationships. Now, there's some values that we call perfect squares, and those are the numbers that are inside these square roots. 0, 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. And those are perfect squares because when you take the square root of these numbers, you get a whole number result, right? So here you have, for example, 64. Well, you know 8 times 8 is 64, which is why the square root of 64 is 8, right? Another way to think about our square roots here is using this picture of stars. So we have 4 stars inside of our box. If we have a perfect square, if it is a square, then what would our side length be? Well, there's 4 here, so we can tell that this side has 2 stars here, and this side has 2 stars. So the square root of 4 equals 2, right? Same thing here. If there's 9 stars in the box, then what would our side length be? And so the square root of 9, you can find out, is 3. The tricky part is, what if you don't have a perfect square? So let's take a look at this example right here of the square root of 20. Here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then we have some almost halves. They're a little less than half. So we'll say like 0.4-ish. 0.4, 0.4, 0.4, 0.4, 0.4, 0.4, 0.4. All right, and then we have like just a little bit here. Little bit, right? So we know that if you were to add all of these up, you would get 20, right? So then in order to figure out what is the square root of 20, well, we know that it's going to be between 4 and 5 because our perfect squares is 16 here and 25 here. It's a number in between. So if we think about our one side here, well, we know 1, 2, 3, 4, and then a little bit more, right? So 0.4, and we can actually use a calculator to check the exact approximation for the square root of 20 is 4.47, right? So if you can take that number inside the square root and imagine making a square of it, what would that side length be? And you can use your perfect squares to help you estimate, and then you can use your calculator to get a more specific, precise decimal approximation. All right. For this lesson, we will be using decimal approximations, and then in later lessons, especially when we get to triangles and the Pythagorean theorem, we'll talk about simplifying radicals. Okay? So here, the distance formula that we're going to talk about is d for distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared, where our x and y are the endpoints of the segment that we're trying to find the distance of. So right here, what is the length of segment AB if the coordinates of the endpoints are A at 1, 8 and B at -4, -5? So we know A is going to be x1, y1, and then B is x2, y2. And I'm going to write out our distance formula. x2 minus x1 squared plus y2 minus y1 squared. And then the distance equals, let's plug all of our numbers in. x2 is -4 minus 1 squared plus y2 is -5 minus 8 squared. So we start simplifying. -4 minus 1 is -5 squared plus -5 minus 8 is -13 squared. We know that that's going to give us 25 plus 169, which equals the square root of 4, 5, 6, 7, and 174. And if we put it into the calculator, 174, you get about 13.2. 13.2. So we know that the distance between A and B is 13.2 units. So using that same strategy, give student example number 1 a try. Okay, let's look at teacher example number 2. It asks, what is the length of segment CD? Now this is almost the exact same kind of question as the first one, but it just doesn't tell us what the coordinate points are. So let's find that first. C here is at -4, 3. And then we know D is at -1, -4. We can again label x1, y1, x2, y2. And then we know that our distance formula, x2 minus x1 squared, y2 minus y1 quantity squared, all right? Distance equals x2, -1 minus a -4 squared plus -4 minus 3 squared. We know that the minus and negative becomes a plus, so we end up with 3 squared plus -7 squared. Distance equals a square root of 9 plus 49. Distance equals a square root of 58. And if we approximate that, we end up with 7.6. So we know that the distance is approximately 7.6. So try this example on your own. All right, now let's move on to teacher example number 3. So how much will you travel if you go from the park to the church to the school? Round your answer to the nearest hundredth. So we're going from the park to the church to school. So here's our park. This is our first location. The church is our second location, and the school is our third location. Now, because it's on a graph like this, it's very neatly ordered, to go from the park to the church, this distance, you can just look at it and you know exactly what that distance is. 1, 2. So from the park to church, it is 2 units. All right? Now going from the church to the school, it goes across. It's not straight, vertical, or horizontal, so we can't use that same counting method. We have to use our distance formula, which means we need the coordinate point of the church, and we need the coordinate point of the school. So here our church is at 2, 3, and the school is at 1, 1. All right? Again, we can use our distance formula. It's the square root of x2 minus x1 squared plus y2 minus y1 squared. And if we're labeling x1, y1, x2, y2, we're getting 1 minus 2 squared plus 1 minus 3 squared, which gives us a -1 squared plus -2 squared. Distance equals 1 plus 4 square root of 5. And if we plug that into the calculator, you get 2.2. So we know that from the park to the church is 2 units. From the church to the school is 2.2 units. We add those together, and we get a total of 4.2 units. All right. So try the student example on your own. Now lastly, for the summary, I want you to look through what we learned today and think about, well, how does distance and time play a role in how we understand our world, right? We only took a small portion of looking at distance. And then hopefully as we go forward in geometry, but also in your mathematical and science careers, you'll gain a more solid understanding of the relationship between distance and time. As always, the summary is expected to be 3 to 5 sentences long with thought regarding our statement of inquiry, as well as using the proper academic vocabulary. Thanks, you guys.